So, we would like to consider the error analysis and convergence of Newton-Raphson method. Before that, we shall define what we mean by order of convergence of a given method. Suppose say we have a numerical method which generates a sequence of iterates which we denote by P0, P1 etc., say Pn. So, that Pn is a sequence of iterates that we generate by a numerical method and it converges to P with Pn different from P. If suppose there exists positive constants lambda and alpha with limit as n tending to infinity of Pn plus 1 minus P by modulus of Pn minus P power alpha equal to lambda. Here Pn is the nth iterate that we have generated, Pn plus 1 is the n plus 1th iterate that we have generated, and these are approximations to the exact value P that we want to determine. Then the difference between the n plus 1th successive iterate minus P in absolute value to the alphath power of the difference between the nth successive approximation to P is equal to lambda, a positive constant. Then we say that the sequence Pn converges to P of order alpha. So, order of convergence of this iterative method is alpha, and the constant lambda that appears here is called an asymptotic error constant lambda. So, let us now see what is the order of convergence of bisection method, because bisection method generates a sequence of iterates. What does it generate? It starts with A naught B naught and it has the midpoint of this interval to be P1, and then it takes the appropriate interval and calls it as A1 B1. So, that this interval encloses a root of the equation and takes the midpoint of this interval, and that is a second approximation to the root of the equation f of x is equal to 0. So, it generates successive iterations, and at every step what happens, the interval that encloses a root of the equation is such that the length of that interval is half the length of the interval in the previous iteration. And therefore, we see that the root P of the equation f of x is such that the distance between Pn plus 1 and P in absolute value is going to be half of the distance between Pn and P when we apply bisection method. And therefore, we have Pn plus 1 minus P divided by Pn minus P is equal to half. So, we compare this with what we have in our definition. So, we have mod Pn plus 1 minus P by mod Pn minus P to the power of 1 is equal to half, and that gives you alpha to be equal to 1 and lambda is equal to half. So, the bisection method has order of convergence to be 1, or we say that the bisection method converges linearly, or it has linear order of convergence, or we say that the bisection method has order of convergence as 1. So, our interest now is to see what happens to the order of convergence of Newton-Raphson method. We already have seen by means of some examples that Newton-Raphson method converges rapidly, and here we observe that modulus of Pn plus 1 minus P is the error at the n plus 1th step, and modulus of Pn minus P is the error at the nth step. So, we have shown that the error at the nth step is related to the error at the n plus 1th step by means of this. Or in general, we have error at the n plus 1 step to be given by some constant c times the error at the nth step raised to the power of say some alpha, then we say that alpha is the order of convergence of the method and C is the asymptotic error constant. So, when we want to discuss the order of convergence of Newton-Raphson method, we would like to obtain a relation connecting the error at the nth and the error at the n plus 1 step in this way and identify what are C and alpha, so that we can immediately make some conclusions about the order of convergence of Newton-Raphson method and also some statement about the asymptotic error constant in Newton-Raphson method. So, let us work out the details for Newton-Raphson method now. So, we perform error analysis of Newton-Raphson method. So, let En be the error at the nth step. What is En? En is xn minus p. Xn is the nth approximation that we obtained using Newton-Raphson method and p is the exact root of the equation f of x is equal to 0. So, En plus 1 will be xn plus 1 minus p. Let us assume that f double dashed be continuous and let p be a simple 0 of the equation f of x is equal to 0. What does that mean? F at p is 0, but f dashed at p is different from 0, because p is a simple 0 of the equation. So, we start with En plus 1. Why? We want a relationship connecting the error at the n plus 1 step and the error at the nth step. So, start with En plus 1. What is it? En plus 1 is xn plus 1 minus p. But we are using Newton-Raphson method and the n plus 1th iterate is given by xn minus f of xn by f dashed of xn minus p. And therefore, we have xn minus p minus f of xn divided by f dashed of xn. This is equal to En minus f of xn by f dashed of xn, which gives En plus 1 equal to En into f dashed of xn minus f of xn divided by f dashed of xn. So, I would like to simplify this, making use of the fact that f of p is 0. This tells me f of p is equal to f of xn minus En. So, that will be f at xn minus En into f dashed of xn plus En square by factorial 2 into f double dashed at xn. So, I shall write the error term as En square by 2 f double dashed of psi n, where psi n lies between xn and p. I know that f of p is 0. So, this gives me En into f dashed of xn minus f of xn to be equal to En square by 2 into f double dashed of psi n. And I observe that this is what appears in the numerator here. So, therefore, we have En plus 1 is equal to En square by 2 into f double dashed at psi n divided by f dashed at xn, where psi n lies between xn and p. So, I observe that I have a relationship connecting En plus 1 and En. What is it? En plus 1 is half of f double dashed at xn divided by f dashed at xn into En square. And if xn is the nth approximation which is correct to the desired degree of accuracy, then this will be half of f double dashed at p divided by f dashed at p into En square, which I can express as c times En square. The order of convergence of Newton-Raphson method is 2. So, Newton-Raphson method has quadratic convergence. Or we say that Newton-Raphson method has second order convergence. Or we say that Newton-Raphson method converges quadratically. And what is the asymptotic error constant? C is the asymptotic error constant. What is that? C is half of f double prime at p divided by f dashed at p. And can you evaluate this? Yes, an approximation to the asymptotic error constant is half f double dashed of xn by f dashed of xn, because xn approximates p, corrects to the desired degree of accuracy. So, the error analysis clearly shows that the Newton-Raphson method has quadratic convergence, and therefore, it is much better than the order of convergence of bisection method, which converges linearly, and that is why the successive iterates generated by Newton-Raphson method converges much faster than the bisection method. So, we now discuss the convergence of Newton-Raphson method. Why do we have to discuss the convergence of Newton-Raphson method? I recall the example that we have considered. We said that there are functions where, starting with some initial values, we are unable to get successive iterates which converge to a root of the equation, and therefore, there must be some conditions on the starting values, so that given a function f of x is equal to 0, and when we want to apply Newton-Raphson method, if we ensure that our starting value, namely initial approximation, satisfies this condition, then by the theorem that we are going to prove, we can be sure of the fact that the successive iterates that we generate using Newton-Raphson method will converge to a root of the equation correct to the desired degree of accuracy. And so, we see what are the conditions that we will have to take care of when we want to apply Newton-Raphson method in finding a root of the equation. So, the result says that we have a function f which is defined, and it is twice continuously differentiable for all x with f of p equal to 0 for some p. So, p is a simple 0 of f of x is equal to 0. If m is such that it is maximum of modulus of f double dashed of x by twice minimum of modulus of f dashed of x, and m is less than infinity, it is a finite number, then starting with any x naught which satisfies the condition that m into mod p minus x naught is less than 1, then the successive iterates that you generate using Newton-Raphson method, namely xn, will always converge to a root of the equation, and you will have a root of the equation correct to the desired degree of accuracy. So, we have shown that E n plus 1 is equal to half of f double dashed of xn by f dashed of xn into E n square. So, modulus of E n plus 1 will be half mod f double dashed of xn by modulus of f dashed of xn into En square, and that will be less than or equal to m times En square. So, we have En plus 1 to be less than or equal to m En square. Let us now obtain E1, that is less than or equal to m E naught square. Then E2 is less than or equal to m E1 square. But I know E1 is less than or equal to m E naught square. So, this will be m into m E naught square the whole square. So, I have substituted for E1 to be less than or equal to m E naught square. So, I will have this inequality. But what is this? This is m into m square E naught power 4. So, it is m cubed into E naught power 4. So, I shall write this as 1 by m into m power 4 E naught power 4. So, it is 1 by m into m E naught the whole power 4. So, we get E2 to be less than or equal to 1 by m into m E naught to the power of 4. Let us write down E3. E3 is less than or equal to m into E2 square. So, it is less than or equal to m into 1 by m square into m E naught to the power of 8, because I am squaring it. Therefore, E3 is less than or equal to 1 by m into m E naught to the power of 8. So, let us now see the pattern. E1 is less than or equal to m E naught square, E2 is less than or equal to 1 by m into m E naught power 4, that is 1 by m into m E naught to the power of 2 square. Now, E3 is less than or equal to 1 by m into m E naught to the power of 8, which I can write as m E naught to the power of 2 cubed. So, I continue this way and write down what is the error at the nth step. So, it is going to be 1 by m into m E naught to the power of 2 to the power of n. And therefore, this error at the nth step will go to 0 as n tends to infinity, provided m times E naught in absolute value is less than 1. So, as n tends to infinity, E n will approach 0 if in absolute value mod m E naught is less than 1, or in other words, if m into modulus of E naught is less than 1, or if m into what is E naught? E naught is the error at the initial step, namely it is x naught minus p, and that must be less than 1. And we observe that that is what we have to show, namely for any x naught that we choose as an initial approximation, if this is such that m times mod x naught minus p is less than 1, then the successive iterates generated by the Newton-Raphson method, namely xn, will converge to a root of the equation correct to the desired degree of accuracy. So, this condition must be satisfied by the initial condition. So, what does the theorem say? The theorem says, if your function f is twice continuously differentiable, and if p is a simple 0 of the equation f of x is equal to 0, if you start with an initial approximation x naught in such a way that m times mod p minus x naught is less than 1, then the successive iterates that you generate using Newton-Raphson method will converge to a root of the equation correct to the desired degree of accuracy. So, you now know how your initial approximation x naught to be chosen. It must be close to the exact root of the equation in such a way that this condition must be satisfied. If this is satisfied, then your Newton-Raphson method converges to a root of the equation correct to the desired degree of accuracy. So, the convergence analysis clearly shows the condition under which the Newton-Raphson method will converge to a root of the equation, and the condition is that the initial approximation x naught is such that it must satisfy the condition that mod p minus x naught is less than 1 by m. So, we now give another result, which is again for convergence of Newton-Raphson method, which tells you that if some conditions are satisfied, then starting from any initial approximation, the successive iterates that you generate by Newton-Raphson method will converge to a root of the equation correct to the desired degree of accuracy. So, let us look into the result which states this. So, the result is as follows. It says, if f belongs to C2 of R, twice continuously differentiable, f is an increasing function and f is convex. What does that mean? A function is convex if f double prime of x is greater than 0 for all x. So, if this condition is satisfied, so f is convex and it has a 0, then this 0 is a unique 0 and Newton-Raphson iterations will converge to this unique 0 starting from any initial approximation. So, this gives you the condition on the shape of the function f. I again recall the example that we had considered. That example demonstrated that there are functions with some shape such that when you start with some initial approximation, the successive iterates that you generate by Newton-Raphson method diverged, it did not converge. So, when you apply Newton-Raphson method and if you want to start with some initial approximation, you should also know about what the shape of the function f is. The theorem says if the function f satisfies the following conditions, namely f is in C2 of R, it is increasing, it is a convex function and it has a 0 and the 0 is then unique, and Newton's iteration method will generate successive iterates which will converge to this unique 0. So, that completes our discussion on Newton-Raphson method, namely we know how to derive this method and we have given geometrical interpretation of the method, and we have used this method to generate successive iterates for a root finding problem. And then we have also compared it with bisection method and shown that this is a method which converges much faster than the bisection method. And we have performed error analysis from which we understand that this method has second order convergence. And then the convergence analysis of Newton-Raphson method tells us that if your initial approximation is such that it satisfies a certain condition, namely the distance of this initial approximation from the root in absolute value is less than 1 by capital M, then the sequence of iterates will converge to a root of the equation. And if the given function f is such that it satisfies some special conditions, it has some special properties as listed in the theorem, then your Newton-Raphson iterates will converge to a root of the equation starting from any initial approximation. So, now that we have understood these details about Newton-Raphson method, we will work out some problems on this method. The problem is as follows. Find an efficient method which is based on Newton-Raphson method, with the help of which you can compute square root of a number, say r. So, let r greater than 0 be given to us. So, what is it that we want? We want to determine what is square root of r. So, call it x. Then we see that x is a root of the equation x square minus r equal to 0. So, I am given f of x as x square minus r, and I am asked to get a root of this equation, f of x is equal to 0, and I am asked to develop a method using Newton-Raphson method, with the help of which I can generate the successive iterates which will converge to the square root of r. So, I determine f dashed of x and write down Newton-Raphson method for obtaining square root of r. What is it? Is this x n plus 1 equal to x n minus f of x n by f dashed of x n. So, it is x n minus f of x n is x n square minus r, and f dashed of x n is 2 x n. So, if you simplify this, then you get x n plus 1 to be equal to 2 x n square minus x n square minus r divided by 2 x n. So, it is x n square plus r by 2 x n. So, n greater than or equal to 0. So, start with an initial approximation x naught. Then you can generate x 1 by substituting for x naught square and x naught on the right hand side. So, that x 1 is given by x naught square plus r by 2 x naught. Find x 1 and then use this again, compute x 2 etc. x n plus 1, and then stop your iterations when the stopping criterion specified in the problem is satisfied. Suppose I say that you make use of some 20 iterations and then determine square root of a number r, then perform 20 such iterations and then you stop your iterations and say the result that you obtain at the 20th iteration is square root of r. So, we have developed a method for computing the square root of a number r, and that is given by x n plus 1 is equal to this. Okay, so, now I ask you to obtain square root of say 1000. And so, I am interested in finding root of 1000. So, I must use this iterative method and find what square root of 1000 is. So, I need an initial approximation. So, I know that this number 1000 lies between 900 and 1600. So, taking square root 30 less than square root of 1000 is less than 40. So, I can take an initial approximation for square root of 1000 to be any number which lies between say 30 and 40. So, let me take my initial approximation x naught to be say 35 and generate what x 1 is, x 2 is etc., and then compute 20 iterations are specified in the problem and get what the value of x n plus 1 right at the 20th iteration, and then call that as an approximation to square root of 1000. So, I want you to work out the details now that we have developed a method and I have given you an initial approximation. You should be in a position to apply this method and generate the successive iterates. If suppose I had given the same problem and I had asked you to compute square root of r where r is 17. So, I am interested in solving what x is equal to root 17 is. Then in that case, I can choose an approximation x naught to be 4. and generate the successive iterates. Xn plus 1 was xn square plus r divided by twice xn. So, which I write as xn by 2 plus r by xn. I start with x naught, which is 4. So, my x1 will be half of. So, this I can write as half of xn plus r by xn. So, this will be half of x naught plus 17 by x naught, that will give you 4.12. x2 is half of x1 plus 17 by x1. So, it is half of x 4.12 by 17 by 4.12, and that gives me 4.123106. Then compute x3, which is half of x2 plus 17 by x2, and I know my x2 is this. When I substitute, I get x3 to be 4.1231056. Let us work out another iteration. x4 is half of x3 plus 17 by x3, and when I substitute for x3, this gives me 4.1231056. So, I observe that x4 minus x3 is such that the result is correct to 7 decimal places, and therefore, I take my approximation to square root of 17 as 4.12311056. So, the iteration method that we developed help us to obtain square root of a real number. So, I shall give some more problems of this type in the assignment, and you can try to work out the details.